Mm-hmm.
Hello everyone and welcome. In this difficult period of life, when COVID-19 coronavirus outbreak continues to evolve in the world, we organize the inspiring online seminar series of TÜBİTAK Research Institute for Fundamental Sciences to mitigate the demoralization effect of the COVID-19 situation on scientific thoughts or science-based actions. It is my pleasure to let you know that I have the honor of introducing our today's speaker, Professor Ralph Wijers, a very well-known world-class scientist from the Anton Pannekoek Institute for Astronomy at University of Amsterdam. He is going to give a great talk on movies of the sky, the hunt for bursting monsters. The talk is part of our astronomy and space science seminar series. At the end of the talk, we will have a session for question answer, where questions can be asked by sending a message through the chat button of the Zoom platform. Professor Wijers' research spans a range from theoretical to instrumental in astronomy and astroparticle physics, with a long-term goal to understand highly relativistic objects in terms of basic physics. Especially he studies the phenomena and mechanisms behind accretion-powered black holes and neutron stars, an explosion resulting from such compact object. He has developed blast wave models on gamma ray bursts and used them to study their properties. He also is involved in searches for rare new types of transient source, in particular at radio wavelengths with LOFAR, Low Frequency Array Telescope, as well as the Amsterdam Astron Radio Transit Facility and Analysis Center Telescope. Professor Wijers has been interested in astronomy outreach since a young age and teaches all levels of courses, from introductory astronomy to advanced graduate courses. Professor Wijers got his MSc from Leiden Observatory and his PhD from the University of Amsterdam. He went on to Princeton on NASA Compton Fellowship and Cambridge on a Royal Society Fellowship, after which he became assistant professor at Stony Brook University before joining the Anton Pannekoek Institute for Astronomy. Professor Wijers is a VC Innovation Research Initiative Scheme and European Research Council Advanced Investigator Laureate and co-winner of the 2002 European Union Descartes Prize for Research on Gamma Ray Bursts. He is a member of multiple national and international scientific governing and advisory councils, and editor of 2 journals, Monthly Notice of Royal Astronomical Society and New Astronomy Reviews. Since 2011, he is the director of Anton Pannekoek Institute for Astronomy. With this, I want to thank Professor Ralph Wijers once again for joining us for this seminar and look forward to his talk. Ralph, you're welcome. Begin your talk, please.
Well, Alikram, thank you very much for that extremely generous introduction. As my good friend Jerry Brown in Stony Brook would have said, please stop, I am already vain enough. But I thank you. Let me see. Ah, yes, I think I am now sharing the screen. So yes, astronomy, as you of course know, basically has kind of 2 duties One is to explore what there is in the universe and make sure that we know the contents and the history of it. And the other is, of course, to do as much as possible precision physics with the things we find to try and constrain the laws of nature better. And so in my studies of transient sources, I do a bit of both. I mean, I look for new kinds of things that suddenly appear in the sky, and then I try to understand them in physical detail. Since these high energy outbursts are often to do with things dying, sometimes my friends jokingly call me astropathologist, because I typically look at objects in the sky when they come to a miserable and violent end. But that is, of course, not the way in which we used to look at the sky. I mean, if you look at the cultural story that most great cultures in the world tell about the heavens, it is often about a very majestic, stately, stable entity. And there is often in that stability and majesty, of course, many cultures have seen some kind of divine glory and so on. And of course, it is true that almost everything in the sky is extremely predictable. If you know what time of day and what month and date it is, you in principle, you can predict which constellations you will see in the night sky at what time. And so almost everything does not change. And then, of course, there are a few things that do change. Like in this image where you see a beautiful skyscape with stars and the Milky Way, you see one very bright object that actually does move, because there's the planet Jupiter. And of course, those wandering stars, which is what planetes means in Greek, where the word planet comes from, have been known since antiquity, right? And at the moment, incidentally, is an extremely good time to see almost all the naked eye planets, because especially in this week, you can see Jupiter and Saturn in the southwest after sunset, and there will be a very close so-called grand conjunction of the two in the evening sky on December 21. You can see Mars in the south at midnight, and you can see Mercury and Venus in the east before sunrise. And especially Mercury is very hard and rare to see well. So if you're interested at all in watching planets, I recommend, if you have a clear morning this week, that you actually go out and try to look at Venus. I did this morning, and it is really impressive and rare. But the point is, this is predictable. Even already the Babylonians could tell you when to expect to see which planet at which location. And as a result, people have been fearful when there were unexpected occurrences in the sky that nobody could predict. There's, of course, the famous story in early Greek astronomy that the astronomer Thales of Miletus actually knew how to predict a sunset, a solar eclipse. But he did not tell anyone. And then when there was a large and catastrophic battle about to start, he managed to convince the battling armies to stop, essentially, because he managed to tell them that something really bad was going to happen, because the gods were displeased. And at that moment, a solar eclipse occurred. So he was a bit devious. He used his power as a scientist to influence things. But generally, change has often been viewed by many cultures, certainly by Western European cultures, as bad news. For example, if a comet appears in the sky, and you can see one here in the background, when a comet appeared in the sky, it was often seen as a sign of an impending disaster. And there is this famous so-called Bayeux tapestry, which depicts the Norman invasion in 1066, when 1066 of the Common Era, when King Harold was defeated by William the Conqueror. And you can see this part of the tapestry here on the left, where you see the soldiers looking at the comet in the sky, apparently very fearful. And then in the next panel, you see King Harold being hit by arrows and dying. Now, of course, whether this was good news or bad news, you can wonder, because it was good news for William the Conqueror. But anyway, comets were often interpreted as signs of something and not necessarily good things. Another very famous one is so-called guest stars. Sometimes a new star appears in the sky. And, oh, I see I made a typo here. Sorry. That suddenly a new star appears in the sky. And this is quite remarkable historically. It is very rare. It happens only once every few centuries. And when this happened in 1054, this was by far the brightest guest star that we remember in history. And it was recorded in Chinese, Japanese, and Korean documents. Here is a famous Chinese text where the yellow indicates the appearance of this guest star. And it was extremely bright. It was visible for more than 600 days, so almost 2 years. And it was even visible during the day for 3 weeks. Which of course means that it is impossible that there was anyone alive at that time who did not see it. And yet in Western Europe, there is not a single record of anyone reporting to have seen this guest star. And of course, we can only guess why that is, but it is quite possible that because these events in Western culture usually meant very bad news, people did the thing that people often do when they see something very bad, namely they look away and they act as if they didn't see it. And then they hope that the problems go away. Now, the other thing, of course, that you can say about classical astronomy, which is, say, from antiquity until about 1930, is that it was all done in visible light. So it was mostly, astronomy in olden days was mostly about recording what is always there and explaining it, and maybe explaining the regularity of things like the orbits of the planets, but that was it. And in rare cases, something changed, as I just noted. And sometimes something changed regularly and all the time. For example, there are some stars that are not constant in brightness, but variable. But for example, the most famous variable star in the northern sky was named Algol by Arab cultures. And of course, Algol means the devil. So even in Arab cultures, apparently a star changing its brightness was not considered to be a particularly good thing. Now, of course, in the last century, an enormous amount has changed in astronomy. And mostly the story of the 20th century and a little bit of the early 21st century is that we have expanded astronomy to cover all wavelengths. Right? As you know, electromagnetic waves go all the way from radio waves to gamma rays. And the visible spectrum that we can see with our eyes is only a tiny fraction of that. And in the last 100 years, we have essentially learned to make use astronomically of almost all wavelengths of light in order to learn more about the sky. Now, of course, that is not always easy because as I remind you in the bottom figure, this figure indicates what percentage of the light can actually pass through the atmosphere of the Earth. And as you see, it is really only visible light that passes through the atmosphere and radio waves. And of course, the fact that our eyes are sensitive to the light that passes through the atmosphere is not a coincidence, because our eyes would not be useful if they were sensitive to a kind of light that cannot enter the atmosphere in the first place. But for example, to do astronomy in X-ray or gamma ray wavelengths or in infrared or in the ultraviolet, we actually need space science. because that's the only way in which we can catch those waves coming from the sky. And nowadays, of course, as you probably know, we do that. So here, superimposed on what I would say is still the best optical observatory in the world, namely the ESO Very Large Telescope at Paranal in the Chilean desert, in the Atacama Desert. We now use things all the way from radio waves. For example, here you see the impressive 500-meter FAST dish that was recently opened in China. It's one of those radio dishes that is very hard to build independently. So this dish is actually located in a valley that has the natural shape of a dish in order to support it. And we have a big radio telescope in the Netherlands that stretches all the way across northwestern Europe that consists of many independent stations full of antennae called LOFAR. But of course, we also have X-ray telescopes such as the Chinese InSight HMXT and gamma ray telescopes such as Fermi, which is a NASA mission. And so the one thing that changes dramatically when you change your view of the heavens from optical light to other kinds of light is this whole image of the sky being very stable. And I can illustrate that by first showing you this image, which is an image of the entire sky in optical light, right? And it's just it is just a projection of a sphere on a flat surface in the same way as you do with maps of the Earth. And so right through the middle of this map, the coordinate system is chosen such that right through the middle of the map runs the Milky Way. And so that is that little band of 100 billion stars that we live in the middle of. And then outside the Milky Way, you see many fewer stars, and you even see these two small blobs here that are the Large and Small Magellanic Clouds that are two small galaxies next to our own. Now, and here is the Andromeda Nebula, for example. That is the first big galaxy like our own Milky Way close to us. But if instead you look at the sky in X-rays in those same coordinates, this is what you see, right? So this is an image of the bright X-ray sources in the sky, and it's the same projection. So once again, the Milky Way runs through the middle of the map, and the center of our galaxy is in this direction. And you see that the bright X-ray sources are largely concentrated in the plane of our Milky Way, and even especially towards the galactic center. But now, look at what happens if I make it, if I make that time change. So here you see one image every day of the X-ray sky. And the moving symbol is actually the sun, which is also sometimes an X-ray source, but not a very bright one. And what you see is that in X-rays, the sky looks more like an American Christmas tree. There are almost no sources that do not change. All the sources change, at least a little bit, and there are even many sources which are almost never there, but then suddenly appear for a short time and then go away again. And those are the so-called transient sources. So in astronomy, typically you call a source variable when you can see it most of the time, but it changes in brightness, and you call a source a transient when it is usually not visible, and then only occasionally when it has an outburst it is visible. But in some sense, it's an instrumentally defined nomenclature, because if you had an infinitely sensitive instrument, you would probably find that, you know, underneath every transient source, there is at least a weak source that is always visible. Now, so in X and gamma ray astronomy, almost all the sources are variable. They are often of very short duration and quite rare. And they can emit a lot of energy. So the typical luminosity, the instantaneous rate at which they emit energy, can be billions of times the luminosity of the sun. And they can be very hot, right? You know, a typical star is a few thousand to a few tens of thousands of Kelvin. X-ray and gamma ray sources can be millions to billions of degrees in temperature. They are, if you look technically, making imaging instruments at these very high energies is very difficult. So typically what you make is kinds of detectors that see large parts of the sky, sometimes even the whole sky, but rather unsharply. So when you do find the source, you cannot tell very accurately what the location of the source is. And that is one of the technical difficulties we have in gamma ray astronomy, especially, that it takes a lot of effort to find out which source had a gamma ray outburst, because initially we do not know its location very well. Now, and then, of course, the key question is, what are these things and why are they so important? Well, why should we care about them? Well, the main reason is because they are powered by the most important force that we astronomers recognize in the universe, and that is gravity. As I need to explain to none of you, energy and mass are equivalent. And most forms of energy that we know on Earth, if you express them in terms of the mass equivalent of the mass that is taking part in the energy, are extremely modest, right? Hydroelectric power typically converts only 10 to the minus 14 of the mass involved into energy. Fossil fuel, only 1/1,000,000th. Nuclear fuel, only 1%. However, accretion, by which astronomers mean throwing matter onto an astronomical object, can convert a few tens of percent of the rest mass energy of the material you throw into energy. And that means that therefore potentially objects with very strong gravity can be the most powerful objects in the sky. Now, an example of that is a supernova. Essentially, as you all know, what happens in a supernova or guest star is that a very massive star comes to the end of its life, right? So what happens is that a star, typically at least 10 times as massive as the sun, explodes because its core has exhausted all possibilities of burning nuclear fuel, because it has burned up to iron, which is the most stable element. And then if it has nothing more to power it anymore, it starts to lose pressure support against gravity, and it collapses. And as you probably know, it then collapses all the way down to a neutron star or black hole. And that releases so much gravitational energy that energy explodes the outer layers of the star. And those glowing hot outer layers are what powers the supernova explode, what powers the visible supernova. So typically, a few tens of percent of the energy that is released is emitted. Most of it is actually emitted in neutrinos, so you never see it. Only about 1% of the energy that is released is converted into an explosion, and 1% of that again is converted into visible light. And yet that produces, so it's only 1% of 1%, and yet that produces one of the brightest phenomena we know in the universe. And so, for example, the famous supernova of 1054 of the Common Era, that was seen as a guest star by the Chinese, at the location of that explosion, there is now a very hot glowing nebula called the Crab Nebula. And that is basically just parts of the exploded remains of the star. And if you look at the center of that Crab Nebula, you actually see one source. You see 30 images here, and these are totally only 1 second. So this is only 1 second of time in these 30 images. And you see that most of the time you see only one source here, but in some frames you see two sources. And this one source that is giving off two flashes is a so-called pulsar. It is a rotating neutron star. It spins around its axis 30 times per second. And what it essentially is a star made almost entirely of neutrons, only about the size of Istanbul, a bit smaller than Istanbul. I always have to be careful. I tell my local audiences always it's about the size of Amsterdam, which is true, but Istanbul is much bigger than Amsterdam. Here you see it projected next to Manhattan. So it's lying on top of Queens here. And so such a neutron star is the leftover core of a supernova. And as you know, a neutron star is supported against gravity pure by the repulsive strong nuclear force. And because it contains 1.5 to twice as much the mass of the sun, but it is smaller than a large city, 1 teaspoon of a neutron star has as much mass as all the buildings in Istanbul. Right? It's something like 10 to the 9 kilograms or so. It's just an enormous density. Well, and then you can, of course, ask, well, how once you have such a neutron star, it no longer has much energy in it if you wait for a while, because it just cools down and it spins down. And then it's dark. So you no longer see it. And that's true. In principle, most neutron stars we see are quite young, and so they still have some energy in them, either in rotation or in heat, that is left from this supernova event. But in fact, it turns out in astronomy there is a way of reviving such a neutron star and making it emit energy again. And that is to do with binary stars. It turns that most stars are not born alone, but they are born in couples or even in multiple stars. It's one of the ways in which our sun is special is that our sun is a single star. And it turns out that maybe only about 10 or 20% of all stars in the universe are single stars. And all the other ones are binary or higher multiples. And so what can happen is that if one massive star is in a binary, that when it explodes, the binary actually survives that explosion event. So our newly born neutron star now has a companion star. And after some amount of time, the neutron star can start pulling material away from that companion star, and that material then falls on the neutron star. And then you get this powerful accretion mechanism to generate energy. All this matter finally gets squeezed into a very small space. You should imagine that this star is about the size of the sun. And so the distance from this star to the neutron star is mainly approximately something like 1 million kilometers in reality. And so this disk of material is maybe a few 100,000 kilometers in size, but the neutron star in the middle is only 10 kilometers in size. And when matter eventually spirals into that center in the neutron star, it gets squeezed into a very small space and all the energy is released there. And that means that in order to radiate a lot of energy from such a small volume of space, material needs to become extremely hot. And that's why it becomes millions to billions of degrees in temperature. And it is even often the case that the neutron star cannot actually swallow all the material that the companion star tries to feed it. And then from very close to it, it blows away part of the material in relativistic jets. So often a neutron star or a black hole even that is accreting has two jets of material that are blown away from it. And these jets can attain speeds that are close to the speed of light. So they are a very relativistic phenomenon. Now, and of course, as you know, perhaps, very small things can also change very rapidly. So one of the ways in which you can see that these neutron stars that are accreting must be very small is because they change very rapidly. Here you see a light curve of an accreting black hole, in this case it is, but it's almost the same for neutron stars. And you see that the X-ray brightness, which is plotted on the vertical axis as a function of time, and you see this entire plot only covers 20 seconds, you see that the source can double in brightness in a fraction of a second. Now, and if you think about it, it is not easy for a large object to change in brightness rapidly. Imagine you have an object in the sky of a certain size r, and imagine that this object all of a sudden, really instantaneously, like a delta function in time, becomes twice as bright. We then do not see that object change in brightness like a delta function, because the near side of the object is closer to us than the far side of the object. So for us, it will take a time delta t that is of order the size over c for us to see the full change in brightness. And this is an argument you can reverse. If you see an object change by a large amount in brightness in a certain amount of time, then you know that the object has to be smaller than about c times that amount of time. So we see the Cygnus X1, which is the name of this X-ray source, change a brightness by a factor 2 in 1 millisecond sometimes. That means that the object has to be less than about 1 light millisecond in size, which is 300 kilometers. And for an astronomical object, that is extremely small. Now, of course, I've already mentioned black holes. They are, of course, the ultimate gravitational source, as you all know. And those we also get in astronomy. And essentially, we get them via the same process that makes neutron stars. We can calculate theoretically that the repulsive nuclear force between neutrons can support a neutron star up to a mass that we think is about 2.5 solar masses. We still do not understand strong nuclear forces perfectly, so we do not yet have a very exact number on the maximum mass of a neutron star, but it is about 2.5 solar masses. And for example, we know that the object in Cygnus X1 is about 10 solar masses in mass. So it definitely cannot be a neutron star. But it again has this property that it emits very bright X-rays, and it has jets. And it emits a very large amount of energy that can only be supplied by accretion. So we know that it has to be a very massive object with extremely strong gravity, and that the only thing that we know like that is a black hole. And of course, then you may ask, well, that is strange. A black hole is defined as an object from which light cannot escape. So how can you tell me that black holes are the brightest objects in the universe? And of course, that is formally true. Light cannot escape from a black hole. But of course, while material is falling towards the black hole, it gets extremely hot just before it falls in. And that extremely hot matter that is circling the black hole just before it falls in, that is the thing that is so bright in X-rays. So it's not the black hole itself, but it is its very close environment, the so-called accretion disk. Right, and just I understood that not all of you are in physics or astronomy, so just to remind you how this works, if you have a gravitating object with a certain mass and radius, you can ask how difficult it is to get away from that object by asking, how fast do I have to shoot something away from that object in order for it to escape from that object to infinity? And that so-called escape speed is given by a formula which is the square root of 2g times the mass over the radius, according to Newton. And if you just casually fill out in the Newtonian gravity formula when the escape velocity becomes equal to the speed of light, you get a size of an object of a given mass that is called the horizon or Schwarzschild radius. And in some sense, by a curious coincidence, if you do gravity the right way, namely according to Einstein, and you ask what is the radius from which light cannot escape anymore for a certain mass, you get that same formula. So maybe slightly by coincidence, the Newtonian formula for the size of a black hole and the correct general relativistic formula are the same. Now, if you ask how big should an object be in order to be squeezed within its own Schwarzschild radius, you find that the sun becomes a black hole if you manage to squeeze all its mass into a radius of 3 kilometers, and the Earth would become a black hole if you manage to squeeze its mass into a size of only 1 centimeter. Now, we don't know whether you can make Earth mass black holes. We don't know of a mechanism by which you could do that in astronomy, at least not yet. But we do know how you can make stellar mass black holes. You can make them by evolving very massive stars and making their cores explode at the end of their lives. So we kind of understand why black holes that are a few solar masses in mass can exist, and why we do not yet know of any black holes that are of a much smaller mass. Now, it does turn out that there are black holes of much larger masses. You probably also already heard of those, and they are typically hiding at the centers of galaxies. For example, here is an image of the center of our own Milky Way in radio waves. And there is a very bright radio source in the middle of our Milky Way, which is called Sagittarius A star. Now, if you look in infrared light close to that very bright radio source, you see some very bright stars. It turns out you have to look in infrared light because there is a lot of gas and dust between us and the center of our galaxy that you cannot see through in visible light. So this view is obscured to us in visible light. So the fact that we can do astronomy at very many wavelengths is essential here in order to study the center of our galaxy. Now, if you look at these stars very close to the center of our galaxy, then one thing you can see is that the stars near the center of our galaxy actually move. And if you watch the motion of those stars very carefully, I will play the movie again. You can see they are traced out here, that actually they don't move randomly, but they move in orbits. And those orbits go around the central object that we cannot see. And because we know how far away this is, and because we therefore know what the sizes of these orbits are and what the periods of these orbits are, the shortest one here has a period of about 20 years. It turns out that means that we can measure the mass of this dark object around which the stars are moving. And it turns out that mass is 4.2 million solar masses. And something that is so completely dark and yet so massive and in such a small volume can, as far as we understand now, only be a black hole. And it turns out that such a black hole at the center of a galaxy is not an exception. it turns out that almost all galaxies have a black hole in their middle. And so we think that making a black hole in the center of a galaxy must be done by a process that very naturally accompanies the formation of all galaxies. And in fact, it turns out that our galaxy has a black hole that is even relatively modest in size. There are some galaxies that have a black hole as massive as 10 billion solar masses in the middle. And you know, for scale, if a massive galaxy has a mass of 10 billion times the mass of the sun, it means that that black hole has a mass of about 1% of the mass of that entire galaxy. In our galaxy, 4.2 million solar masses is less than 100,000th of the total mass of our own galaxy. So on the scale of our galaxy, the mass of this black hole doesn't matter very much. But at the very center of our galaxy, it dominates the motion of those stars. Now, as you probably know, this discovery was rewarded in this year by the Nobel Prize in Physics. It was shared by Roger Penrose, who did very fundamental work in proving that there are natural ways in physics to actually create black holes, and to Reinhard Genzel and Andrea Ghez, who actually demonstrated that at the center of our galaxy there is such a black hole. Now, another famous black hole that was in the news in the past few years, I'm sure you also heard of, that is the black hole in this very massive bright galaxy called Messier 87, in which a bright jet was discovered by an optical astronomer, the American Curtis, a century ago, almost exactly a century ago in 1918. And as you probably know, in this galaxy very recently, for the first time, we imaged the shadow of a black hole in the very center of it. So what you see here is a material orbiting the very center of that galaxy, the black hole around it, and the black hole casting a shadow in the light emission of that hot material. And even in the last 2 years, we've been able to demonstrate that the center of light of that ring around the black hole changes slowly, which means that material around that black hole is indeed moving. So now, of course, the question you can ask is, are these monsters rare? And of course, it depends. You could call them rare, because in our Milky Way, for example, there are 100 billion stars, but we only have one supernova per century. And we only have a few hundred of these X-ray binaries and a few thousand pulsars. So in some sense, relative to normal stars, these phenomena are indeed extremely rare. On the other hand, you could also call them common, because even though there is only one such massive black hole in our Milky Way, there are 100 billion galaxies in the visible universe. So there are as many of these supermassive black holes. And for example, with one supernova per century in our Milky Way, it means that we have 1 billion supernovae per year in our universe. And so that is 30 supernovae per second. So in some way, if you look at the universe as a whole, they are not so rare at all. But it turns out that there are even much rarer explosions than supernovae. For example, gamma ray bursts, which are one of my own research specialties. There are only about 1,000 gamma ray bursts in the entire visible universe per year. And that means that they are about 1 million times rarer than supernovae. Now, they were discovered serendipitously by spy satellites in the 1960s. Those spy satellites were actually created to monitor nuclear weapons explosions. And the first time that we really solved what these gamma ray bursts are is when an Italian-Dutch satellite had this Dutch instrument on board, which was for the first time able to localize very precisely such a gamma ray burst. And it localized the gamma ray burst to this very faint optical speck of light in the sky, which turned out to be a distant galaxy. So what we discovered in the year soon after 1997, when this happened, is that these gamma ray bursts happen as a kind of extreme supernovae. It turns out there are two ways to make them. One way is that you have an extremely massive star that explodes at the end of its life, and it makes a very massive black hole. And that massive black hole then eats up part of the rest of the envelope of the star, makes two big jets that explode the star, and those jets emit a gamma ray burst. And that is what we see. And another way it turns out is that we can see, if you have a binary star in which there is not one neutron star but two, those two neutron stars can orbit each other, and in orbiting each other emit so-called gravitational waves, which are another prediction of Einstein's theory of general relativity. And due to that emission of gravitational waves, the orbit slowly shrinks, and eventually the two neutron stars collide with each other. And that releases an enormous amount of energy, which can again make a jet and a gamma ray burst. And it turns out that this latter mechanism was very spectacularly confirmed in 2017. In 2017, with the so-called LIGO and also Virgo gravitational wave detector, we managed to detect these gravitational waves or ripples in space-time that originate when very strong gravitational objects orbit each other. And these gravitational waves actually emit an enormous amount of energy, but because they happen so very far away, the effect of it on Earth is actually tiny. And from the time that astronomers and physicists realized that such gravitational waves might be produced by colliding neutron stars, it took 40 years to actually build a detector that was sensitive enough to detect it. So this is a story that nowadays we always tell our funding agencies, that they should expect that funding fundamental physics is useful, but they should not expect that the results from their funding are visible tomorrow. I mean, doing fundamental science, as I'm sure all of you know, requires a lot of patience. Now, what happened of course, in 2015 is that these detectors first discovered gravitational waves from colliding black holes. But a few years later, on 17 August 2017, they actually proved this connection between gravitational waves and gamma ray bursts, because what it turned out is that LIGO and Virgo measured this typical gravitational wave chirp signal that you see in the bottom panel. So they saw the oscillations of space-time that were becoming higher and higher in frequency, that indicate the merger of two gravitational objects. And then 2 seconds later, American and European gamma ray satellites actually measured an outburst of gamma rays from that same direction in the sky. And so this is a phenomenon that, as far as we know, can only be caused by the merger of two such neutron stars. Now, another prediction that you can make if two neutron stars merge is that some very neutron-rich material should be ejected from this explosion, and that neutron star-rich material should also create optical and radio wave phenomena at later times. And that was indeed also seen. Here you see the galaxy in which this neutron star merger happened. And in the outer regions of this galaxy, indeed, within a few hours, we saw a small optical source appear. And this optical source became brighter, and later it faded away again. And if we take a spectrum of this optical source, we see that whereas almost all the optical sources in the universe are made almost 100% out of hydrogen and helium, like our sun, which is made of hydrogen and helium and only 2% of more massive elements, this exploding source was made in very large parts of lanthanides and actinides, so of the most massive, very neutron-rich elements. And in fact, it is probably the case that almost all the gold in the universe, and platinum and uranium and thorium and such elements, excuse me, probably almost all those very massive so-called R-process elements are probably made in these explosions. So if any of you wears a golden ring like my wedding ring, then we can be sure that we carry something with us that must have been made in the merger of two neutron stars, or maybe in the merger of a neutron star and a black hole. So all of us carry with us in our daily life something that is that comes from extremely rare events in the universe. And it is very nice that by this spectroscopy we can actually determine the chemical composition of such an explosion that, of course, happens at a distance that we can never touch. I mean, if astronomers and physicists actually had access to 30 Earth masses of gold, we would, of course, never have to ask anyone for funding again. And of course, at this point, my economist friends would comment that if we had access to 30 Earth masses of gold, the value of gold would immediately drop to almost zero. So it wouldn't work, that little trick. It would only work if we told nobody else about it. Okay, so it turns out that these extremely hot outbursts of relativistic material actually produce radiation at all electromagnetic wavelengths and also in all types of particles. So the end, such a merger of two neutron stars probably produces gravitational waves, cosmic rays, neutrinos, and all kinds of electromagnetic radiation, all the way from radio waves to neutron to gamma rays. So it's worth our effort to try to detect these rare sources at all wavelengths. And in fact, I myself am trying to do this at radio wavelengths, and I'm using the radio telescope LOFAR, which is essentially a computer-connected network of very simple radio antennae like this. And so all these antennae receive radio waves from the entire sky. They measure the voltages due to these radio waves, and by niftily combining those in a supercomputer, by a technique that is called radio interferometry, we can actually construct radio images of the sky that way. And because unlike most radio telescopes, these antennae see the entire sky, we can also see the entire sky with this radio telescope. So I can actually make fisheye lens images of the entire sky. So here you see a radio image of the entire radio sky above the Netherlands. And I can actually make such an image once every second. So here you actually see a movie of the sky in radio waves. And so you see some very famous radio sources. This radio source, for example, Cassiopeia A, is the leftover of an exploded star. And this radio source, Cygnus A, is actually such a black hole in the center of a very bright, very massive galaxy. Taurus A is actually the Crab Nebula, so it is also a leftover of a massive star. Sometimes you say also human-made stars. This is a satellite that is geostationary, that flickers there. So you see that it does not orbit with the rest of the sky. You see the sun is also a radio source. The planet Jupiter is also sometimes a radio source. And what I'm doing with this experiment is I'm actually trying to find very rare radio outbursts that also happen sometimes in the sky, but unfortunately my experiment has only just started. So at the moment, this is more of an advertisement for science that I'm going to do in the future than telling you the result of science I have already done. And so with that, I have actually come to the end of my talk. So I would like to thank all of you for your attention. And maybe some of you have some questions.
Thank you very much for this comprehensive and very exciting talk. Please ask questions or send your questions through chat button to the speaker.
Let me stop sharing my screen, then I can let me switch on my chat. So yes, I have it. So you can also use the blue button for raise hand if you want, whichever way you like. Okay, I see a raised hand from Beren. I hope I pronounced the name correctly.
Yeah, it is okay.
So please ask your question, but you will have to unmute yourself.
Hi, I want to ask a question about a black hole news, actually. I saw a news about a black hole and there's writing something like that. A kind of light went out of the black hole. I couldn't find any other news about this. So do you know something about this? I just want to learn this. Thank you.
Okay, thank you very much. I'm afraid I'm not aware of this specific news item. It may refer to the fact that we have recently discovered some of the so-called X-ray and gamma ray transients, which some of those being black holes, where they suddenly had an explosion because some material was accreted onto it. Sometimes that accretion onto black holes happens more or less continuously, and then you see such a variable source. But sometimes also there are black holes which are more isolated, and most of the time they do not accrete material. So they are dark. In fact, we have no way of seeing them. And sometimes suddenly, for example, they eat up a passing star in a so-called tidal disruption event. And then for a short time, maybe for a few weeks, they become a very bright source, and then they become dark again. Any other questions?
There's a message question from Ömer Faruk Çoban.
Okay. This is a very good question. The electromagnetic burst of the gravitational wave event 1708-17 came 2 seconds later than the gravitational wave merger event. That is true. So there are 2 ways in which you can get interesting science out of that. The first way in which you get interesting science out of that is that you can say the delay was only 2 seconds. And because this event was 100 million light years away from us, we can conclude that if you only have 2 seconds of time difference over 100 million years of light travel time, that is the most accurate measurement to tell us that the propagation speed of gravitational waves in space is almost exactly the same as the propagation speed of light. So it is a very fundamental physics measurement in one way. So the fact that gravitational waves move almost exactly with the speed of light is a very nice result. Now, of course, you can ask, well, they didn't arrive at exactly the same time. That can actually possibly have a very mundane astrophysical explanation, namely that after the 2 neutron stars have merged and the gravitational waves have been emitted, it takes a little while. The explosion then starts and it moves out, and it takes a little while for that explosion to generate the energy that makes the gamma rays and to emit those gamma rays. And it is very plausible that that could be 2 seconds. People who have tried to do the calculation find the theoretical time delay could be anywhere between maybe half a second and 10 seconds or so. So probably that 2 seconds is just the delay that happens because it takes some time to make the gamma rays out of the energy. Okay, thank you. Any other questions? A question, is it possible to have a binary system made of 2 black holes? Yes, it is. And in fact, the interesting thing is we did not know of any single such binary until we started measuring gravitational wave events. And in fact, we have now measured several tens. I think we are now up to more than 30 gravitational wave events that are detected by these gravitational wave detectors. And almost, and all except 1 or 2 of them are actually merging binary black holes. So the answer is yes, but unfortunately we only discover these binary black holes when they stop being binary black holes and they merge. The only thing that we are still waiting for, that we have not yet discovered with any certainty, is a binary that consists of 1 black hole and 1 neutron star. And if we try to make predictions for how many of those things should form, if we know how many binary neutron stars and binary black holes there are, it is about time that we do find the gravitational wave merger event that consists of 1 neutron star and 1 black hole. So this is probably something that is going to happen in the next few years. Is it possible that some of those bursts you've mentioned could trigger seismic activity on Earth? No. It turns out that these gravitational wave events are so weak that they would not even knock the ashes off your cigarette. I mean, there is really no way of seeing anything, any effect of those gravitational waves arriving on Earth, except with these very sensitive multi-100 million gravitational wave detectors. I think the only effect that we know of that such explosions have on Earth is that the strongest gamma ray bursts and also the nearest supernovae can increase the flux of gamma rays and the flux of radioactive particles on Earth. And we think that we have discovered in the past decade 2 pieces of evidence in the fossil record, one in a very old ice core drilling and one in a tree ring that is about 800 years old, of a very anomalous enhancement of carbon-14, or I believe beryllium-10, that may have been caused by a supernova or a gamma ray burst going off very close to Earth and causing the deposition of some extra radioactivity in the atmosphere of the Earth. So fortunately, most astrophysical events, even though they are extremely violent, happen very far away in an extremely large universe. So they are close enough for us to enjoy, but far enough away for us not to fear them.
So more questions.
Yeah, there is one. How do scientists find out about the time origin of an event in space? That's a very good question. I mean, I think that one of the things that is quite confusing in astronomy is what do we mean by now? Because if I tell you that we saw this gravitational wave event on the 17th of August 2017, of course, that is the time when the radiation that was emitted by it arrived on Earth. But in fact, the event happened 100 million light years away, and that means that the event really happened 100 million years ago. So one of the interesting things in astronomy is that if we look far away in distance in the universe, we actually also look back in time. So astronomy can describe and write its own history because we don't have to dig for ancient artifacts in the earth like archaeologists in order to find out about history. We can find out about history now by looking at things that are very far away, because far away in astronomy is also long ago. Now, the way you find out how long ago it was is by measuring how far away it is. And there are all kinds of astrophysical techniques by which you can measure the distance of an object. And if you know how far away the object was, then you also know how long ago it was. And that's just because you know how fast light travels. As you may know, actually, historically, the first time in history that we ever measured the speed of light was from the orbits of the moons of Jupiter. There was a Danish scientist, Ole Rømer, who was working at Paris Observatory, who was noticing that if you measure the orbits of the moons of Jupiter around Jupiter, you sometimes find that those orbits seem to happen a little bit late or a little bit early. And he realized that whether they were a little late or early depended on how far away the Earth was from Jupiter at that time. And actually from that time difference, he made the first measurement ever in history of the speed of light. And it was a fairly accurate one. Okay. You are muted, Alika. We cannot hear you. You are muted. Now I can hear you again.
If no more questions, maybe we can stop here. What do you think?
Yes, I think just there was one more question. In the video from the radio talk, there was somewhat looked like me as noise, sinusoidal ring shaped, if I saw correctly. Could you comment on this? Yes, indeed. I mean, making these all-sky radio images and calibrating them properly is technically very difficult. So you noticed indeed very well that there are some there are some artifacts in those radio movies which are actually not astrophysically real, but they are basically relics of calibration uncertainties in the radio detectors. Let's see. Is it possible to reach the speed of light? No, I'm afraid it is not. I mean, Einstein's theory of relativity, if it is correct at least, tells us that material particles can come as close to the speed of light as you like, but they can never exactly reach the speed of light. And what do you think about the news that came from Venus and the Moon? I think with the news from Venus, you probably mean the news of the detection of possible life on, or at least a molecule that may originate from life, the detection of phosphine. Is that what you actually mean? Yes, well, that is not my expertise at all, so I should be very careful. The cautionary comment that I can make is, since this result was made public, a few colleagues of mine at Leiden Observatory have redone the analysis of the observations, and that has cast some doubt as to whether the phosphine was really detected on Venus, or whether maybe this detection is spurious, that it was an instrumental error. So if there is phosphine on Venus, it may be very meaningful, but at the moment the cautionary note is that it may not be there. How can we know the direction of rotation of the black hole in M87? We cannot know that directly, but we know that almost certainly the jet that is emerging from the disk around the black hole must be perpendicular to the disk and therefore in the same direction as the axis of rotation. So that is how we can know. We can measure the direction of the jet. But then we need, in addition, to add an element from theory, and that is that it is theoretically plausible that the rotation axis falls in the same direction as the jet. Okay. Well, thank you very much for those very interesting questions.
It seems that no more questions, yeah?
It seems so, yes.
Maybe then we can stop here. What do you think? Thank you so much for joining us and for joining us for this seminar. It was an honor and pleasure.
Oh no,
I hope we will meet in person as soon as this coronavirus settles away.
Well, I hope so too. I have to say very honestly that Istanbul is still on my and my wife's bucket list for beautiful cities in the world to visit. So I very definitely think that we will make use of the occasion to visit in person fairly soon after that is possible again. And it was entirely my honor and pleasure to give a lecture at your institute. So thank you very much for the invitation.
Thank you. Thank you.
Okay. Thank you very much, everyone.